we can start.
Okay, I think we can start. I give you for time, Pak Budianto, for opening. Thank you.
I will host these meetings. Good morning, everybody. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Pagi ini, this morning, we will have a very fruitful discussions with the experts, tsunami experts, world-class experts. Dr. Eric Mas. He's originally native from Peru. Are you from Peru or from Chile?
Yes, from Peru. Yes.
From Peru. Yes. If we know about the many historical sites, ancient sites from Peru, he's from there. And Dr. Eric has been in Tohoku University since 2011, and he pursue his PhD, get his PhD from Tohoku University, specialized in tsunami modeling and strengthening the core teams of tsunami engineering laboratories. Now becomes IRIDES, and he is now also assigned to geomatics geomatics related to tsunami. That means the informations the geo related to topography, related to bathymetries, related to boundaries of these tsunami modeling. And is also promotes the evacuation model, which is important to us when we have this tsunami. We not only concerns about the waves, how the run-ups, but also how we could save life of peoples. That would be one of the reasons why we have this discussion. Even though the time was set was very short, it was about 1 hour, because I'm wondering when after 12 you will have a lunchtime. Otherwise, it will be more flexible if it's not your lunchtime at 12. Maybe, but also we could have another discussions later on, if you think that would be. Without do I have enough introductions for you, Dr. Eric?
Sure, no problem. I also can speak.
Okay, yes. Without further ado, I would like to have our distinguished lecturers to have his presentation. Dr. Eric Mas, please, time is yours.
Okay, thank you very much. Yeah, my name is Eric Mas. I'm from Peru. I actually came to Japan in 2009 to study tsunami engineering in the same place as Budianto, I guess, with Imamura Sensei. So I probably, when I arrived here, you were leaving Japan.
Yes, I was.
Right. So we never had the chance actually to share the laboratory. But yeah, we have the same background. I came with the idea of
dia bantuin engineer dulu. Gimana? Udah selesai?
Aduh, second.
Apanya, Pak?
Bisa
yang ke Pak Daniel.
Nah, terus
lanjut.
Udah selesai?
Belum.
Apanya lagi?
Tinggal dikit-dikit.
Aisan bisa di
Yep.
semua.
Okay, so and then but actually when I came here, one of the topics that was not really taken so much care was the tsunami evacuation and how to model that. There were in the past kind of very few simple models, and then so I started to work on my PhD studies on what is tsunami evacuation modeling. Then I discovered agent-based modeling, which is very related to what is social simulation, not really engineering simulation. And it was very difficult actually to bring the social kind of way of thinking to the engineering faculty, because you know engineers we like. I'm also civil engineering, so my mind has to explode a little bit to change my view of what is kind of a physical model, right? You know, tsunami simulation, you have an input and then you have an output. It's just like that. You have the equation and it's gonna be always the same output. But in agent-based modeling, you have the same input and you can have different output. So that is one of the tricky parts to understand in agent-based modeling. Okay, so let me share my whole screen. I think I'm disabled. So can you enable for me to share screen, please? And I will show you well, what you guys can take from here.
Okay, please, Eric.
Okay, great. So let me share the whole screen because I will just move around a lot. So first, I will just give you the one link to a GitHub repository that I created the other day, actually, which is where I put the whole model packages, right? So you can actually download yourself and try yourself, and that will be probably the way you can better learn faster. The first thing I recommend you to do is go to resources and then look at this, which is my PhD thesis, right? It's probably old already. It's 10 years ago. Yeah, I guess 2012. Yeah, 10 years ago. So, but I think it will give you an introduction of what is agent-based modeling and how we created this kind of model. We call tsunami evac because there was already a tsunami model in Tohoku, the Tohoku University numerical analysis modeling for inundation, right? Which is the tsunami simulation model. And we just created the evacuation model and just make the name as like that. It was never so famous, so it just stayed like that. It was always one because we never got the chance to do so many versions of this. But here, what the thing is that you can see what is the kind of data we use, the process that it uses, what kind of layers, what is the logic of the model, and then how can you actually use the model, okay? And then some cases we use, like actually when I was studying 2009, in 2011, the Great East Japan earthquake happened, and I was my second year of my PhD. So I was already working in evacuation simulation, actually in an area in the coast of Tohoku, right? So we had some kind of questionnaire service to this area to see how people react in evacuation, etc. And but suddenly the earthquake happened, the tsunami happened, and a lot of this area was washed away, was totally damaged. And most of the people we were working with for questionnaire service, some of them died in the tsunami, okay? So it was very difficult after that to actually gain contact with all of these people because they moved away. The whole area changed a lot. So we have to rethink the whole thesis, right? The whole study. But always keeping the goal of developing a tsunami evacuation model. So we use the 2011 as a way somehow to verify if the model gave us some kind of consistency. We use some other cases in Peru, in my country, where I have some kind of information also, just to apply to some kind of specifics of tsunami mitigation, like trying to see what is the response time, the casualty estimation, or what is the shelter demand, some things that you can do with the model, okay? And then that's it. And then you have an appendix where it's kind of a user manual, very simple user manual, that probably is kind of the thing that you will be interested. Some of the questionnaire we do, the source code, actually, I don't know if it's in this version, but the source code is already in the repository, so you can take a look. And yeah, that's kind of the main idea of what is the study, and this is the kind of background of other models that were developed at the time, okay, from 2000 maybe until the time I developed this model. And what kind of characteristics those models have, what kind of characteristics this model have, which some of them were not really agent-based, but some of them were kind of GIS-based or network-based, kind of traffic simulation related, okay? Then you will see, well, in evacuation modeling, one of the key aspects is the human behavior or the agent behavior. Actually, how you are going to incorporate the kind of behaviors you want to see into your model. So one of the first things you have to bear in mind is that this model is not going to work for everything you want to do in evacuation model. It's built for some kind of a specific purpose, and it's probably going to answer some specific questions. Like, for example, what is the timing of evacuation in this area based on this kind of behavior, right? But if you want to assess some kind of other kind of question, like, I don't know, what is the effect of people going first to their home, pick up their stuff, or go back to the school, pick up their children, and then evacuate, which is a different kind of behavior, which is not incorporated in this model. Okay, so some I wouldn't say limitations because it's just a different purpose. So you have to take the model probably and just change a little bit, a lot of your agent behaviors to incorporate what you really want to do. Okay, so just bear in mind that what you want to do cannot probably be assessed by this model. Okay? So the model is something like this. Okay, we have an agent behavior. We have a spatial database, which is GIS data. So we use generally vectorial data. You can use shapefile, I mean, like the polygons or lines or something like that, to create your environment. Okay, we call it human database, but actually it's kind of some idea of based on questionnaire service, some idea of the population, the area you want to look in, some idea of how they will react, what kind of preference they have for evacuation, if there's vertical evacuation, horizontal evacuation, what kind of proxies you can use as parameters in your model. Okay, and then the main model is developing NetLogo. Okay, I will show you what is NetLogo. The tsunami model, which is the tsunami simulation, this is loosely coupled, meaning that you have to run the tsunami simulation apart. So you first decide your area, you run your tsunami simulation, you get the output, and that output is the one that you use as an input in this evacuation model. Okay, it's not a fully coupled, meaning that it's not running at the same time. This is just two-step. Okay, you run the tsunami simulation, and then you run the evacuation simulation. Okay, and then you get your outputs, snapshots, videos, whatever you want to do. Okay, this is kind of how the model looks. I will show you the model in a minute. Okay, it has a graphic user interface, which is one of the probably advantages of NetLogo, that it's very easy to create your graphic user interface and communicate that with your code. The code is also very simple and easy the language is very simple and easy to learn. So, but the limitations of NetLogo, of course, are the size of your area cannot be so large. Okay, so because it's gonna be very heavy in computation. Okay, so that's one of the probably limitations. But if it's a fairly small area and not so many agents, or the behavior you input into the agents are not so heavy in computation also, yeah, it's a good prototyping software. Okay, so you can prototype your ideas, your model and behaviors in NetLogo, and then just move to some other powerful language like, I don't know, Python, C++ or something. Okay, so here I explain what are the spatial input data we use, generate some shape files. Okay, I will show you that. A case is already in the repository, so you just can download, run, and test. okay, and then just replace your data and see what's going on. Well, it's convenient that all your data is projected in the same projection. It can be whatever projection, but it's not necessary. As long as your data has, let's say, the same size, okay, which is probably, or at least your tsunami output is on the same size and scale that your input data, your environment, okay? If there's a different projection, there's no matter, because NetLogo will reproject everything into the same, fit everything into the same screen. But anyway, just for maybe being organized, you can do the same projection. The case I'm sharing in the repository has not the same projection, just to show you that it's possible to use different projections, okay? Then what are the inputs for the agents? These are the parameters that probably you have to decide and see or test, or the parameters actually you can work with. And then, yeah, the explanation of how the model actually works, what kind of theories we are using to, for example, generate the start time of evacuation of people, which is very critical decision. I mean, there are several approaches. I mean, you can use, for example, that there is in environment, there is a triggering of your decision for evacuation. Like everyone says, like, for example, if you see damage around you, or you see people around you evacuating, that is a triggering for you to evacuate. Okay, that is one approach, but this model does not use that approach. This model, what it uses, we use something that we call it departure curves, which is kind of just a distribution in time of how many people will evacuate a long time, okay? And because this is agent-based and we use some kind of stochastic modeling, we have two boundaries of these. Well, this is a discussion on if we use stated preference, like if you ask people how they prefer to react, or if you ask people how they actually reacted. So this is a discussion on what is the suitability of using one or the other. Well, the conclusion is that it's better to use both, but in a stochastic way. So we develop a kind of criteria to create these two boundaries. Okay, one boundary is based on, let me see, there should be an image of that. I don't know. Okay, it's not here. There should be two boundaries of this. One boundary is based on the stated preference, meaning that how people think they will react. Like most people think they will react faster than the arrival time of the tsunami. But actually, how people reacted is very close to the time of arrival of tsunami. It's like people try to wait for the last minute to confirm that it's necessary to evacuate. Okay, but so the real behavior is going to be in between these two. That's why we theorize. Okay, and that's why we created different evacuations using fast evacuation and a slow evacuation and in between. And then we average out all the cases to obtain what is kind of what we say the most probable behavior. Okay. Then how we assess for the routes and things like that. Okay. But probably it's better for you guys to look at yourself, and I would just show you what is going on with the model. What else I have to say? Okay, NetLogo. Okay, this is NetLogo. Okay, actually this is the homepage of NetLogo, and there's a lot of information. You have a lot of documentation. It's very easy to learn. You have this kind of interactive dictionary for beginners, or some models that you can look at. Some of them are very abstract models. Some of them are very easy to see. Well, I don't know. Do you have Japanese, Persian, Czech, anyway, Chinese, whatever? But then you have this NetLogo download. Okay, you have many versions that you can download. The last one is 6.2.2. Actually, the model was developed in 5.0.1. As you see, quite old, which is around, is not even here, I guess. but it's already in 6.22, and we just tested, and it seems that it's running, which is, I don't know, I was impressed because many commands or many things have changed in the logo that likely probably we are not using different, or there is a kind of back compatibility maybe from the 6.22 to the 5.01. I'll show you the code in a while. Okay, so the case test that I'm putting here is kind of an area in Tohoku, which is, it takes around 15 minutes to run. So as you see, it's a little bit slow to run a 1 hour and 10 minutes evacuation. So from the earthquake to the arrival of the tsunami in this area was around 1 hour and something. So we had to run 70 minutes to be sure that the tsunami will arrive. Okay. So all that 1 hour and 10 minutes of evacuation takes about 15 minutes computation time. Okay. You can increase this. Well, there are several ways. Probably you can optimize the code or use some kind of increase the memory of your virtual machine, because this uses Java virtual machine. This is not, nothing to do with if you have 20 cores, it's not going to be faster. Okay. And then, well, you can put here and see probably an animation how the model actually. I mean, you can create this kind of video. The black dots are supposed to be. This is of course accelerated. The black dots are supposed to be people on foot, while some very fast dots. I don't know if there is here or if this is only. Probably this is only pedestrian. But you can combine pedestrian and vehicle. Oh yeah, see, these very fast, those are vehicles that actually try to go around this. And that tsunami coming, the red dots are casualties. Some, if you see, not here, but if you see some white dots, that means that there was some kind of congestion in that place, but it's not anymore. At some point of the whole evacuation, there was some kind of congestion. So the idea of those white dots was for me to identify which areas have possible bottlenecks because of traffic or congestion. But if people actually are stuck in those congestion until the tsunami come, or just stuck for a while. Okay. Okay. Let me. I have some kind of publications on this. The first one is this one, which is kind of the first original introduction of the model and the test in the Tohoku case. So we have one of the first models. This is 2012, so it was very new on the source model. So this is not probably the best source model, but this was the best at the time. Okay. So as you see, and probably if you have some kind of experience in tsunami simulation, you can do what we call nested simulation. Okay, you have a large region or large domain, okay, that generally, of course, fits your source, your earthquake source, okay, and then you have some other smaller regions until you get to your finest region, which is the one you want to focus the simulation. This is because we little by little increase the resolution, okay, and actually the propagation and all the equations are much more accurate. That's the idea of increasing the resolution of bathymetry, topography, and things like that. Okay. So the main idea is you probably can use your smallest region, okay, of the computation as your area for evacuation simulation, okay, or a portion of your smallest region as your area for evacuation simulation, okay. It's up to you. The resolution we recommend is at least 5 meters in the resolution of your evacuation simulation, okay. But you can do even smaller. One of the how to say limitations or something of doing very high resolution is going to be that you will have here much more resolution, and you will have much more heavy computation. Okay, it's going to be probably a little more better in your agent representation, environment representation, but it's probably going to be a little more heavy on your computation. Okay, so you have the tsunami simulation, you make your simulation, and then you start to do your evacuation model. Okay, this is kind of the main introduction of the model. Some simplifications we did, like for example, we did this is a test of people coming from one side, people coming from two sides. This has a very high pedestrian collision avoidance behavior. Okay, so this is much more detailed movement of pedestrians. Okay, but because we didn't want to incorporate such kind of heavy computation in every time in the model, we used a simplification. So I ran these several times and measure the density of people around this area. Like theoretically, you can put around this number of people, but actually in the dynamics of the real behavior, you actually can fit not the 100%, but 70% of because people is moving and they have some kind of personal space that they don't want to collide so much. Okay, so based on that, I made a simplification of that, and that's the rule that we introduced in the model. Okay, so pedestrians are not avoiding that, they don't have a higher avoidance behavior, they have a simplification equation of that. Okay, simplified equation of that. Similar to casualty probability, meaning that when tsunami comes, we use some laboratory experiments. They have, for example, under different inundation depths, what is and tsunami velocity, what is the probability to keep your body stand up. Okay, so based on that, we did a binomial regression, a logistic regression, and this is our curve that we use to decide when an agent becomes casualty or not. Okay, because we have in the tsunami simulation, you can have the depth output, which is you can see tsunami database here, and you can have these ASCII files are the outputs. Probably it's not going to show here. Oh yeah, it's going to show. So these are the outputs of the tsunami. Okay, and this is the depth, and you can have depth and you can have also velocity, right? This is depth outputs. You're looking at here. Because we have this, you can make this regression and use that kind of proxy to calculate during the simulation who is becoming a casualty, who's not. Honestly, I will say that there's not so much effect on this. I found that tsunami comes so fast that the number of people that actually in tsunami survived are very, very, very small. Okay, so of course we know that in reality there are so many cases that people survive tsunami because they were inside a car, because they cling to a tree, or some other kind of, but we cannot model that in here, right? Because it's too much behavior. So this is how we generated the casualty. Okay. So as you see, based on that, you cannot expect from this model to have 100% accuracy of what is going to happen or what happened in the real situation. Okay, but it's going to give you a fairly good estimation. Okay, that's what we can say. What else we have here? Oh yeah, you need some kind of idea of how people will behave or expect to behave. Okay, so you can have this as your fast boundary of behavior, and then based on the expected arrival of the tsunami, okay, you create this other curve using probably equation is around here. Let me check. There should be an equation around here. There's a I think I showed you in the paper. Sorry, in the thesis. There's equation for, it's a Rayleigh distribution and you use the tsunami arrival time as the mean of the distribution. That's how you create this curve. And then you run the model like 1,000 repetitions or more. And this is going to be randomly assigned at the beginning of the model. And then this is kind of the average of the simulation. This is actually how we, out of all the runs, how we averaged the whole simulations, right? And that's kind of the most. What else you can use? Well, the good thing on agent-based model is that you can look at the very tiny information okay. And then you run the model, and this is kind of the output of the model. Oh, sorry, yeah, this is the output of the model. TEB, it means tsunami evacuation building. So in this case, we have 2 exits and 1 tsunami evacuation building. And you can log, or you can see how people is coming to each building, or how vehicles are exiting one of the points you set. So this is good information, maybe just to see, okay, at what time, how many people I will probably have in my evacuation building, kind of a managing of shelters, if you want to take a look on that. This is what I told you about the white dots, then where there was some kind of congestion, but finally released during the simulation. People did not die here, but it's some areas we have to take care. Okay, and this makes sense because the shelter was here, and this is kind of and one bridge is here, so all of this area comes around here, and this is kind of the exit. So it's the main road you can use to actually exit this area. So it makes sense that it's going to be overcrowded. But also this road is overcrowded because it's the most preferable to go through this other exit. So that's how we can identify which roads we have to take care of. Okay. I don't know what's that. Yeah. So then this is one of the first papers that you can see here, right? The second one is how we apply the model in La Punta in Peru, which is kind of the same idea. You have your source, you simulate, you have your parameters, population, and some kind of behaviors you want to check. But in this case, what we did was we checked the tsunami evacuation buildings. Okay, this is a peninsula, several buildings in the area. Some of them by capacity, they can allocate the whole population. That's what they say. But the problem is that the spatial distribution of these buildings might not be the best. So how can we test that? We test with the evacuation model. What happens if people evacuate horizontally? What happens if people evacuate vertically only, or a combination of both? And how the demand and the capacity of these shelters compare to the average of our simulations, okay? So we can say that some buildings are highly preferred than others, and basically because they are located probably in the middle, or some very large buildings are located towards the sea, which people will not maybe prefer for evacuation. And then what we can do is map here what is the capacity demand. Okay, so what buildings are highly demand but have low capacity? What buildings have a large capacity but very low demand? So we can then discuss, okay, we should probably create another building, so we should probably organize the evacuation somehow. And that's how you use the model to aid your tsunami mitigation activities, okay? Another one, probably this is got nothing, not so much to do with evacuation modeling. It's just for you to know how I did the simulation of the area I show you here, okay, of this evacuation area. But the other one is this one, probably is the last one, which is kind of a summary of the. So probably you know Abdul Muhari. Yeah, I studied with him in my in Tohoku University. Yeah, and here is kind of a summary of the cases we use. This is the tsunami, the Tohoku area, Arahama, which is the one I'm sharing in the repository. We test one time at the beginning in Padang as a request from AMSA. And but the problem here was that it's a very big area, large, very crowded area. So we had to split the model in 3 parts and test the model like at 3 different models and then aggregate everything. So it's kind of another way to do large areas. This is Thailand because one of all my colleagues also is from Thailand, which is Anawat. And also we wanted to do something in his area. And this is, if I'm not wrong, Pakarang Cape, if it's the name. And this is, here we wanted to test, this is a very flat area and the evacuation areas are very inland. So the problem here was if it's possible to use vehicles and how much vehicle we better use or we don't use. Because after 2011, it was recommended not to use vehicles. What we thought for some cases, it's probably necessary to use vehicles. And this is one of the cases, okay? How the use of vehicles impacts the evacuation and how the evacuation behavior impacts the casualty. This is one of the outcomes. This is another case in Tohoku, using the 2011 information. Because here, what happened was that many people evacuated 2 times. First evacuated here. After some kind of information of the tsunami getting higher, they decided to go out to evacuate farther inland, but it was too late and some of them were caught by the tsunami on the way. So we tested, tried to verify if the model gives us some kind of consistency with the case of the 2011, which is this case. We kind of found very similar casualty estimations, which makes us kind of rely on the model. And we test another case on different behavior. Okay, so this is one of the advantages of tsunami evacuation modeling, that not only you can try to verify what happened, but also you can try to see what other kinds of behavior you can incorporate, or you can see, or you can change the environment and see what is the effect on that. And then if we're using a different kind of behavior, we found that there can be a reduction of fatalities with that behavior. Okay, so yeah, you can take a look at this. This is the one I showed you before, that the capacity demand is another way to see it. And yeah, and that's it. This is kind of the summary paper of some of the applications we used for that. Okay, so probably you can start with this, maybe? Yeah. Okay, so that's it. Yeah, you can also take a look in I think the code is also shared in this kind of repository for codes, if you like, but it's the same as the GitHub I gave you. The good thing is just it has a DOI, so you can reference that the other way. Yeah, this is me, and maybe it's just okay. So this is the model, right? I'll show you now. We have some time, so I'll show you a little bit of the inside of the model. Okay. Oh yeah, this is just to show you that this is the tsunami output that I'm using, because actually the I don't know if I have here. Oh yeah, I think I will put you in this kind of this is the data you have in the repository here in a special database. Okay, the shape files. I will put later this map in the resources, okay, folder, which is just a map of what you have. This is the land, this is the sea, this is the urban, which actually we are not using the urban. I mean, the buildings are not used in the model. They are just painted just to understand it better. And the streets that you can bring the streets as lines or polygons. Probably polygons are better. I mean, you can just do a buffer of your street in GIS and then import that shapefile. And then some evacuation buildings, which are actually two entrance for this building. And then some exits, which are 2 exits. So actually, you know, tsunami came all the way until here. Okay, this is this is the area of Tohoku. Oh, I did it too much. This is Tohoku. Okay, and this is Sendai. I'm around here right now, here. But if we go close to the coast, this is oh yeah, that's the one. Yeah, this one. This is the area. Yeah, this is the area we're using. Of course, this image is right now. Okay, so that's why it's only just remaining. But at that time, this was the area, how it looked like. Okay, a lot of buildings around here, all of them washed away. And this is the, this is the building that was used as a evacuation area, which is actually right now this one. Okay, that had 2 entrances, which is actually right now museum. Okay, if you have the chance to come here, you can go here and see how this area was affected by the tsunami. Okay, yeah, so that's why, because we didn't want to model all this area until the inundation zone, we put these 2 exits here and just assume that vehicles that are exit this way, they have chances to get here faster. Okay, so yeah, you have to do some kinds of assumptions in your model to actually make it work better or efficient for you. Okay, so this is the data you will have. Okay. The model is this is the model. And let me put the code. So what you can do in these versions of the logo now is that you can actually take the code tab outside, so you can see the modeling environment and the code here. Okay, so this is the model. Generally, what you do is just you just download everything and then open the file tsunamievac1.net logo, and then just to test, you can just set up. And when you set up, it's gonna bring all the shape files we saw in QGIS. Okay, it's gonna tell you, okay, the special data was loaded at this time, population data was loaded this time. Yeah, I think this is too much. I don't know why this is. Now it's reloaded very fast. And then this is how you have, and you have already your population distributed. Okay, I will show you how the model is doing that. You know what? And then you press go, and then the model is going to start calculating. Okay, if you see here, the ticks are moving. Okay, but sometimes it's gonna stop because it's making some calculations. You probably will not see much around here working on because of probably the rate of update. Okay, but if you want your model to work faster, you can just take these view updates off. Okay, you're not going to see anything here, but probably you're going to see some here, some changes here, which is how things are going on in the background. And if later you want to see actually what happened here, you can do a movie, which is here. You set this on, and then at the end you will have a movie, like an animation, okay, of this, and then you can check. Okay, so that's my recommendation. You can do this in real time, look at that, but it's gonna have much more time, and it's gonna be very small changes at a time, so it's gonna be very difficult to see something. So my recommendation is to turn off these, make a movie, and just look at the movie. Okay, later. So you just put this, go take a, I don't know, coffee or something, right? A Java coffee, and then just come back. Okay. So what things you can input here? You can input the kind of distribution of your population, like number of kids. I call kids. Anyway, you can do your assumption of what is the age of kids. I mean, I don't know, let's say under 12 people, and then teens will be from 12 to 16 or whatever you want to do your kind of distribution. What is the difference between these? The difference is that each of them has different way of speed. Okay, the speed, the moving speed is different. Okay, but another thing is that you can just do the same kind of agent. Like for example, everyone is adults. Everyone is one kind of speed, and then just make it simple for you to understand. Incorporate some vehicles like this. Have some cars. So what happens when you put vehicles here? Let's say there are 50 cars. My assumption in the model that you can change actually here is that a car fits 4 people in average. Okay, so what I do is just I will have 200 people out of these adults put in a car. Okay, that's how the model is working. This is the mean of the distribution of your evacuation preference questionnaire, meaning at least the 50% of the population have already decided to evacuate at 7 minutes. That is the meaning of this. This ETA is the expected tsunami arrival time, which is 67 minutes for this area. And this is the total simulation time, which is 70 minutes. So 3 minutes after tsunami arrives. Okay, that is the meaning of these 3 parameters. Here, random shelter means that if you want your agents to decide to evacuate to any shelter, so if you put this on, it's gonna be to evacuate to the closest shelter. Okay, so this is on. Everyone will look for the closest shelter in an Euclidean way of calculation. Okay, just directly, not through a route, just not through the shortest path, just the closest one in my radius. Okay, but if it's off, it's just any out of the list of shelters I know. Tsunami on means that you have some kind of tsunami simulation data and you want this to be uploaded in the model. If you don't have a tsunami simulation, you can do the evacuation model. You can turn it off, put maybe just this time as you expect, and then maybe here you put the same time of the arrival of tsunami, like 67, and then the model will stop just when the tsunami is supposed to arrive. Okay, and you will not need to have any tsunami simulation. Okay, so you can use the model without any tsunami modeling. On snapshots is just if you want to have this kind of snapshots. Okay, if you see this is not coming. Okay, because in the output we have other kinds of snapshots that actually shows that. Okay. Okay, and these snapshots, well, these or much more rated snapshots are used to create the animation. Okay, this is how model 67 is just a way of calling. You can change the name here, model. I'm using this to be sure that the name is going to change. Okay, so model, or you can just put whatever case 67 is going to happen. Okay, and then just this is just a distribution of how your agents are going to evacuate. So if you see, there's a lot of agents deciding evacuation around 15 to 20 minutes, and there is some very few at the end. Okay, this is the Rayleigh distribution, not the cumulative. This is just the probability distribution. Okay, I'll show you this one. And then this is the output. Okay, you have how many people have already decided to evacuate, how the evacuation buildings are being filled right now, or people are coming out of the exit, vehicles are coming out of the exit, and how people is safe right now, and how many casualties. Right now, there's no casualty because tsunami has not arrived yet. So you will see this picked at the end of the simulation. And that's it. That is how the model looks and works. Okay. So what is the inner of the model? This is what you're gonna find when you put code tab, and we have actually 2 libraries created, just not to pack everything in the same tab. So I'm using GIS extension just to bring the shape files that I need. Pathdir, because I'm using several directories, so this is just to access different folders. And V is an extension in that logo to create the animation. Okay. I don't know. This is kind of explanation. The model was developing in logo, actually in 4.5 something. At the end was 5. And I updated to 6.1 sometime. I guess 2 years ago. I had some time updated. But I just checked that 6.2.2 is also working. Okay. So we have some global variables. Generally, these variables are related to the environment. Patches are the grids. Okay, that's how the logo call the squares of your environment, the grids. Okay, they call it patches. So I have some patches for the land, for the urban, which is sea, which is a street, whatever, just to differentiate the attribute of every patch. Some variables for the model, which is a scale, because it depends so much on if you have a 5-meter resolution, 10-meter resolution, or what kind of resolution is your environment or your data. So you can actually scale your movement of the agents. Probably is around here. So let's say if I have a scale, this is just to see set patches size 3, meaning that this is going to be this size. If I have a scale of 2, meaning that if I have higher resolution grid size, 2 meter by 2 meter, set patch 1, because what is going to happen is that this window is going to be larger, and I'm just reducing the size of the window so it can fit in your screen. Okay, so but you can change whatever resolution you have here and change the size so this can fit better in your screen. But this is important. I don't know if I'm using that somewhere else. Yeah, this is important here because you're scaling the velocity that we are using for each agent. So this is 1.68 meters, but because my resolution here is 5 meters, I have to scale this value so in the logo is going to be represented adequately. Okay, so that's why this scale is very important. Okay. Counter is just because the names of my output were very weird. So counter I put like this because when you see this kind of tsunami database, you will have a format in the name, which in our case my format was out and the snapshot time or something like that. This is the 53,900 snapshot in that tsunami simulation. Okay, so I just use the same name, but anyway, you can use whatever name you want here, but you have to change this and then change maybe the initial out, which somehow comes somewhere. Probably it's coming here. You see here, I'm creating the name here. The tsunami file name is out plus my counter, which is going to change. That's why it's a variable, and then the extension. And that's how I create the next file name that I will bring in the next step. Okay. But if you have a different name, I don't know, some people use ELR, I don't know what is that. Some people use, I don't know, whatever output you have to use, whatever name you want to put is, but you need to have some kind of counter, something. And if you see, this is 0, 1, 2, 3, 4, this is just 1. But if your counter, if your snapshot is every 5 seconds or something like that, then you have to change here 5. Because it's going to change 5, 10, 15, 20 or something like that. Okay. In this case, it's 1, so just leave it like 1. Because data is at 0.5 seconds. Well, actually, this should be 1 second. Anyway. Or I don't know, I don't remember my resolution. Maybe that the simulation was 5 seconds output, like every 5.5 minutes, maybe. I don't know, 30 seconds. Anyway, what I think is this is 1 second actually. Yeah, this should be 1 second. 55.2, yeah, this is kind of 3 hours. Anyway, then yeah, you have the file name. That's how you use to create a file name. And this is the maximum capacity of pedestrians, maximum capacity of cars in grid, which I'm using here. You remember that I did a test of pedestrians going and then how many you can fit in one area. And finally, it was not 100%, it was a 70% of people. So that this is the 70%. So how many pedestrians can fit in one grid of my scale? Okay, so in a 5 by 5 square meter, 70% of pedestrians can fit. In a 5 by 5 square meter, only 0.07 cars can fit. This is just to account somehow for this kind of physical crowdness in the scale you have. Okay. So generally, if you use 5 meters, don't change this. If you use a different resolution, you can well, you can change or you can just use the same because the scale is here. Okay, so it's gonna be always a 70% of your scale. 70% of the area you have in your grid is gonna be the maximum capacity. Okay. Well, this comes from here, where the population. This is just to save in a different way how many people were saved. So you can have in here you will have plots for kids, teens, adults, elders, and they will have different behavior of decision, behavior of being safe, or behavior of casualty. And that's it. So what does the model do? Okay, agent-based simulation is a lot of object-oriented programming. So you have a lot of objects, which in this case are called breeds, okay, which are the turtles in the logo. Okay, so different kinds of agents that do different things. So this is an object car, well, a group of object cars. Okay, and then generally you use a lot of functions to give them some kind of rules or behavior. Okay, so the first is to set up, which is actually this bottom goes here, clears everything, set initial values, which goes to here. Okay, so if you see, I'm calling, like if you are related to Fortran or something like that, you have call subroutine something. Okay, if you are related to, I don't know, Python, you have define function something. Okay, it's similar. You call with this, you call this function, and then all of this is going to be run. Okay, this is kind of initializing the variables and starting to create a movie if you want a movie. Move to a different folder to start to log some kind of outcomes. One of the logs we have here is the plots actually are logged like this. Okay, you have step by step what is the number of people evacuating. Well, right now it's still 0, I guess. Casualty, and this is casualty. Oh, okay, some casualties around here. Or the safe. This is actually the same plots that you're looking at in the environment right now. These plots are exported later as files, so you can actually look at them. Okay, if you don't want to use the graph, or you want to plot yourself from the raw data. And this is a kind of a log file that I use to kind of track what is going on. So this is the car, something is now located at this coordinate and wants to go to this coordinate, but finally end up in this coordinate. If those are the same, means that arrive to the goal. If those are different, means that at some point it didn't arrive. L0 path, L1 path means that what is the initial grid, the initial length of the path they want to take. TD is the time of decision for evacuation. TSH is the time for something that I don't remember right now. Let me check. 2.6. Time for shelter. So it's the time he arrived to the shelter. ZT is the tsunami depth. So if this is -99 means that no tsunami depth was there, so this guy was safe. If you have a tsunami depth of some kind of value, probably he was a casualty in some point. Okay, and then 0 once means if it's casualty, I guess. Yeah, here for example, once is casualty and the tsunami depth was 1.66. So this guy was washed away by a 1.66 tsunami. Okay, at which point or something like that. So with this kind of log, you can do whatever you want. I mean, you can do some kind of regression, you can do some kind of, I don't know, machine learning model, whatever you want to use that input for whatever purpose you like, okay? If you want to log more information, you can change this, incorporate something, some variable, and then when we do maybe export records. Yeah, when you do export records, you include that kind of variable here, and then you are logging much more information in your model. Okay, if you want to assess something like this random seed, it's for the model to behave the same randomly every time. But let me know. I don't know if, yeah. In this case, I just set it here because that will make that every time you run the model, you will have the same output. Okay, this is just for reproducibility. But actually, when we use the model, we comment out this because what we want is for the model to create many kinds of scenarios. Okay, so we want actually the randomness to work. Okay, if you want the randomness to work, you comment out this, and now same input will not necessarily have the same output. Okay, if you put this to work, same input will have the same output. Okay, this is how you can replicate, share your results or something like that. Okay. Yeah, and then is load spatial, like how you can actually bring the shape files to your model. I told you that it doesn't matter much of the projection because here is going to envelope everything and fits in the world, whatever projection they are in. Okay, and then you can just use. That's why my recommendation is that these guys should have the size of these guys should be kind of multiple or really similar to the size of your world. Okay, the number of columns and number of rows in your tsunami output should be at least somehow similar or multiple of the world. So it can actually, it's gonna fit better, it's gonna look better, it's not gonna be wider or stretch or something like that. That's just for visualization purposes. Okay. Then how the population is loaded. So based on how many people you mentioned you want, we create these people, we set a dimension for these just to look at them bigger or smaller. We set some kind of speed, I mean, reduction according to the age or the capacity, like 80% for kids or 70% for elder people. You can change this as you wish. You can change the basic velocity as you wish. So this is free to change. Right now it's hard coded, but you can access here and change as you wish. And then how we create this, we ask this all these pedestrians. Okay, we created what we call a pedestrian here. And we move these ones to whatever urban patch. So whatever building, okay? So this is a very randomized allocation of pedestrians. Okay, we are not using, there's no other version here, but we are not using census data or some kind of other real allocation of population. Okay, we have the total number, and out of that total number, we just distribute it randomly wherever we can possibly put them. Okay, and we give them some kind of decision for evacuation based on this Rayleigh distribution. Sorry, this one. Okay, we give that tsunami decision based on this Rayleigh distribution, which is this way of doing Rayleigh distribution. And then, well, some heuristics. The heuristics here means when the agent looks for, I'm here and I want to go to the shelter, they have to look for the route. Okay, we use what we call A-star simulation. Okay, A-star algorithm, which is kind of an extended version of a Dijkstra looking for the shortest path. So the difference is that A-star can give you the shortest path or can give you whatever path, because it has some kind of heuristics. Heuristics meaning that how we assess or understand the environment, you can understand like that, like how you can estimate the distance from here to somewhere else. Okay, in the model is how they calculate the distance from that point to the shelter. Okay, it can be in a zero, meaning that it's a shortest path, or it can be using another kind of heuristics of how they calculate the distance, Manhattan or something like that. Okay, I think I'm using 5, which is not around here. I don't know why I put 5 here. Random 5. Okay, so in this case, the heuristics are going to be some of this. So not all agents are assessing their path the same way, meaning that 2 agents in the same position not necessarily will have the same path. They will probably go to different paths. Okay, that's why we included the heuristics, because everyone not always decide the same just because they are in the same location. Okay. And then similar for cars, as I told you, if we have cars, we assume that they have 4 people in each car. What else? Movie, whatever the movie, and then okay, and then once you finish the tab, this is the go. This is kind of the main program. Okay, where you put go. I think already finished, right? So we already have our outputs here. There was no inundation. I don't know why. Okay, or I think I stopped. Yeah, I stopped at some point. Okay. Yeah, because when you change something here, this is going to stop. That's why it stopped. Okay, so this is the goal. What we do is we ask all the turtles, meaning all the pedestrians, to decide if they're going to evacuate. It's just looking at their decision time. If it's the same time of the model, they start to evacuate. When they start to evacuate, they decide a shelter. Okay, how they decide the shelter? So that's basically if you want them to find the closest one, or you want them to go randomly. Then they have to search for the path from here to the shelter they decided. How they use it? They use the A-star algorithm for that. And then for cars, there's a small difference. They have to follow a different path, which is because they have some kind of a faster speed. They have to run faster. Okay, so in one step they go farther than pedestrian. That's the meaning of it. Then we found the route to the shelter. We check if there is a tsunami output that we have to include here, and then we just output the model. Okay, we do some kind of outputs. If there is a tsunami to check here, this is going to check also for the casualty estimation. Okay, otherwise it's just people is going to just run, and then the simulation stops at some time. Update text, meaning okay, the text that you see here for the clock maybe. Okay, and the movie, just movies of snapshots. I'm just saving movies and snapshots. Do plots is to update these plots that you have seen here, these plots. And then once the simulation finishes, at the time I decided, this is all what I'm exporting. I'm exporting all these files that I showed you here in output, okay? I'm just creating those files, kind of the wrapping up the final simulation, all the files I had. I'm just exporting. Some outputs are already being written in real time. So if the model crashes or if you have some kind of freezing of the model, at least you will have some kind of outputs, okay, until that time. So, but not so much of these. Maybe you can just do here and just export, and that's how you can get as much as you can if the model freezes or crashes, right? But if the model freezes or crashes, at least this is going to be available until the time it freezes or crashes. Okay? Then you can see if there's a bug or something. And that's it. And that's it. The rest is just small functions that actually have to do with adjusting the speed based on how many people is around you. If it's possible to move or not to move based on the topology, meaning that pedestrians and vehicles cannot move out of the streets. They just have to go on the streets, which I'm assessing this based on the color, okay? Because the color is color of the streets are green, okay? So based on the green, people can move only on the green, okay? Once they come from the building, which is they can work on the white. Once they enter the green, the only thing they can walk in are on green patches. Okay, that's how the topology is working here. And then I'm adjusting tap capacity. This is if you have some kind of capacity in your buildings, or you just want to see how much is the capacity. But this is how this is going to be plotted based on that updates. Okay? How people is getting in the buildings. Plots updating the outputs, updating the outputs. That's it, I guess. That's how the model works. That's all what the model is. Yeah. And yeah, well, this is supposed to be 15 minutes, but I cut it in the middle because I did something here. But what you will get, luckily we haven't seen any crash right now, any bug or any problem. So it means that it's gonna run and you will get these outputs, okay? You will get also these outputs, okay? And you will get these outputs, okay? The files, and also the video. I haven't put the video in the repository. You won't see the video because it's a little bit big, okay? And there is some kind of constraint for free accounts, okay? But you can run yourself, and then you will have the video similar to what I'm just doing right now. That's it. Okay.
All right, that's excellent presentations. So many information, resourceful and details of the step-by-step on how we set up the model for this evacuation model. And before we, I would like to ask you how many times you still have for your time.
Yeah, no problem. I can eat later.
Okay. All right. Thank you very much. Okay. Maybe before we go to Q&A, question and answer from audiences, I would like to have three things here. First, we would like to have pictures, photo, image, picture together. If everybody were still here, maybe some few are already left before we saw 65. Now it's already 52, but it's okay. We could have this. Bisa Pak Isan mungkin? Bisa ya?
Yes, yes. Maybe a question first before we are take photo.
Oh, question first. All right. Okay. Okay, we are now open for questions. You could ask question. Everybody might raise questions in Bahasa Indonesia, and maybe I will try to translate it in the local language.
You can ask in Indonesian. I don't understand. Selamat pagi. I only know selamat pagi.
Silakan kalau ada yang ingin ditanyakan nanti mungkin bisa saya bantu untuk terjemahkan. Or you may ask in English directly.
Okay, I have a little bit of question.
Yep.
I think this is already proper to all algorithm, but I think we have some different characteristic of the city. This is must more deeply study, or we can change the little bit the parameter.
Yeah, you can change the parameters. Actually, well, the model is you can change whatever you want and incorporate something. For example, one of the things that the model does not take into account is if you see most of the areas I have used the model are flat areas. So topography, it has no effect here. Some other models, they take into account topography. So you can bring kind of a DM file or a elevation file and create in your model some kind of restrictions if there is some slope coming to your agents, like reduction of your velocity. Okay, but that's going to be the purpose of your model, right? That's so take this model as a kind of a baseline to create or extend the model to something else. You can easily you can change the shape files and input those shape files and test the model as long as your shape files are within one same region, and that's going to be easier. But if you want to see something specific like other kind of behavior or other influences of the environment into your agent behavior, you have to change the code.
Okay, thank you very much. It's very important for me, for us, I think, for direction evacuation in coast area. I think.
Yeah.
Oke. Pak Budi mungkin.
Iya, terima kasih Pak Ihsan. I think there are a big chunk of this tsunami, I mean, inputs that will be used, that we have to prepare prior to running this evacuation model, and this takes a lot of efforts to make these two things work. Do you have any suggestions how we
Well, it depends on, again, it depends on what you want to see, but honestly, what I've seen after using the model and studying the evacuation, there is not so much need to have the tsunami simulation to assess tsunami evacuation, because what we really want to see is that people evacuate before the tsunami arrives. Okay?
Oh.
So you can try to test the model until the time of arrival of your tsunami, and then whatever is staying on the streets or whatever is staying not evacuated, it's probably going to be washed away in a couple of minutes. So you can probably give them 2 more minutes or something like that if you want, but it's just a matter of simple 2 to 5 minutes for this whole tsunami to wash away your small area. So it's not going to be much different to incorporate or not incorporate. So why you want to probably incorporate tsunami simulation? It's probably if you want to see another kind of effect. Like if you have a very high tsunami simulation, probably, I don't know, like when you consider buildings in your simulation and you want to see the flow of tsunami in the streets, that's probably going to be that's going to make some kind of difference in the evacuation model. In that case, probably you need to take care on the tsunami simulation and incorporate that in the model, because you want to see some kind of specifics on that, right? But otherwise, I don't see much problems on avoiding the tsunami simulation and just put tsunami off and then just run your evacuation model and see what kind of evacuations are going on. It depends on what you want to see, right?
All right. I think that answers my questions, and few of my colleagues that think possibly the impact of tsunamis on
Yeah.
along coast.
Yeah, but for example, another way is right now the model uses this distribution for evacuation, right?
Mm.
But what if you want to make some people not to react on this distribution, but if you want to them react on the movement of the sea, for example, assuming that people looks at the sea and if they see some kind of change, they will evacuate. Okay. In that case, you have to create those specific agents that will react to the model. And then you have to incorporate tsunami simulation. And when some kind of threshold happens, they evacuate. Okay, that's another way to probably need the tsunami simulation in the model.
Yeah. For example, in 2004, Kaolack or Thai area was not aware of this. Any earthquake, they don't feel it, and information from Indonesia was not sent directly or even in that day, because all the measurements are limited to the seismograph that has been broken. All of the seismograph have been broken. The papers are torn out.
Yeah, and that's, for example, some of the other things that you cannot see in this model, but you can incorporate in this model in a way that, for example, I'm not using any kind of warning system, right?
Yeah.
Because I already have the distribution. My assumption is that at any time of whatever reason, everyone is going to evacuate at some point. Okay, even if it's because tsunami came, even if there was a warning, or because they just evacuated because of the earthquake, whatever, I don't care. I just put a distribution. But if you want to see that problem of tsunami warning triggering and the dissemination of the warning across the village or the city, then you have to change the model for that. But at least the basics and the movements are there in the model, so you can build on top of that.
Yes, that's correct. Thank you, Sensei. I think the models is not only for tsunami. It could be for any buildings evacuations. It could be
probably, yeah, but yeah. For example, flood can be, but the problem is that timings are different. Hurricane, the time is, for example, larger, so your distribution is going to be larger. Evacuations are probably going to be much more in the vehicle than in the pedestrian. Flood is very fast. It's probably you need the warning or kind of a way to account for these kind of weather warnings. So yeah, the model dynamically works for any kind of evacuation in any kind of disaster, but the behaviors the agent has, they are much more tailored to tsunami. So I have to be careful if we want to apply the model in another disaster.
Yes. Bapak Ibu, mungkin ada yang ingin tanya lagi yang lain? Silakan. Nggak apa-apa bahasa Inggris, nggak apa-apa bahasa Indonesia, nggak apa-apa. If my students, they have many questions. In fact, when I discuss about tsunamis, and it's so many questions they have.
So yeah, why don't you put all the questions in one document and then send it to me, and then when I have time, I start to reply all the questions. As much as I know. No worries, anytime.
Yeah, and also we have this Sakura science programs that now we are with having the program with Nihon universities, but maybe in the future we are thinking to have, say, tsunami science. Sakura science programs. Sending students to Tohoku universities and to have these site visits to the tsunami museums and all the rest of the structures that remains of the 2011s. That would be something that I in discussion with Udo Sensei for maybe when we are there, we are awarded, maybe we will visit your laboratory as well. And
Sure.
help it.
Sure, we are all here, so we are willing to share. We also have, with Indonesia, we have every year iWest, right? Organizing the iWest.
Yeah, I was, yes, with
So we can meet also there and share.
Shakwala University.
Yes, yes.
Yeah.
So if you guys want to share kind of research, or we can create a session for evacuation if you like.
All right. Ada lagi adik-adik Bapak Ibu mungkin yang ingin ditanyakan? Pak Marsa mungkin ingin ada yang ditanyakan Pak Marsa atau Bu Dini, silakan.
Okay, thank you very much. I think it's enough for Eric. This is time for lunch in Japan, I think.
Yeah.
That's right, Pak Budi?
Yeah, I agree.
Okay.
No worries, I had a good breakfast.
Okay. I have. I am very thank you, Eric. Very glad and very thank you very much for it's today for Eric Mas. It's just very important for us and for Indonesia. I think it's a very good opportunity. Looking forward for continue relationship. I think between Pak Budianto and then research with Eric. I think. Okay. Thank you very much, Pak Budianto, and thank you very much, Eric-san.
Yes, thank you very much. Thank you all for coming.
Thank you. Thank you.
Okay, Pak Budi, maybe in closing.
In closing, yes. Yes. Thank you. It's very having your discussion time is long effort to set up. Sometimes we have very limited time, and time differences are restricting us to have this fruitful discussions, and we are very grateful that you are able to have this time and extra times for this tsunami discussion, which is, I think, we are Indonesians, Indonesian along coast of Indonesia. We already know this belt of fire or ring of fires that potentially subject to seismic gap, for example, Sunda Straits or southern Java coastlines, even the Sumatra and further east to the Papua and Nusa Tenggara. And this area would be our subject of studies in due course, I think in the futures. Then we would like to have these cooperations with the Tohoku universities, in particular IRIDES and civil engineering and environmental engineering departments, with civil and engineering department of Bakrie universities. And we look forward to having close cooperations in the near futures, and we wish you all in the good health. Stay alert, keep wearing mask, even though propaganda is not recommended anymore, but we still think the pandemic is still there for end of this years, I think. And we look forward to having more fruitful visits and meetings regards to evacuations model by the end of this year, or maybe full years and next years. So we thank you for the geomatics in IRIDES labs for times and patience to set forwards with us from Bakrie Universities, and our audience from KKP, from BRIN, from UNCRIS, and from many other places.
Did you
that
take your photo?
Yeah,
Okay.
we would like to take a photo. Paisan, silakan.
Okay, maybe the audience can be on cam for the take the photo for Mori, I think.
Ya, adik-adik silakan dibuka.
Okay. Okay, I have slide 1.
Oke.
Okay. Okay, I think enough.
Alright. Oke.
Okay, thank you very much.
Thank you very
Thank you
much,
very
Erik.
much, Erickson.
Arigato.
See you.
Ya.
Okay, thank you. Terima kasih banyak semuanya, audiens. Mungkin yang bisa belum mengisikan absen untuk sertifikat webinar kali ini. Oke.
Iya.
Saya akan masih open untuk Zoom-nya mungkin untuk bisa ngisi sertifikat. Terima kasih sebelumnya. Selamat pagi. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Makasih Pak.
Waalaikumsalam. Terima kasih, Pak.